All right. So remember, the main thing is the core is where fusion takes place, where hydrogen is turned into helium. The radiative zone is where those photons are free to travel, and then they reach this more opaque region. Opaque is just you can't. The photons get absorbed, and that's called the radiative zone. And then once that heat reaches the photosphere, it's turned back. It transforms back into light. The heat turns back into light, and of a different frequency, actually, a much lower frequency, and then the photons will encounter the chromosphere, and of course the corona, and then go zipping out into space in three dimensions, right? In three directions, in all three dimensions. All right. So one of the things that we measure is what's called the luminosity, and we do this with stars too. And in fact, we're going to call the luminosity of the sun, which turns out to be 4 times 10 to the 26th watts. That will turn out to be 1 solar luminosity. So, stars that are putting out more energy than this will have more than 1. Stars that are putting out less energy than this will be less than 1. All right. So anyhow, so that's what luminosity is: the total energy radiated by the sun, and we can actually capture a small portion of this, of course, because it's radiated outward in all directions. And so when it arrives at Earth, it's spread out, and in fact, we on Earth, on the surface of the Earth, we get about 1,400 watts per square meter. So all this energy, which is a tremendous amount of energy, by the way. It is actually a measurement of power. Watts are units of power, but in 1 second. That would be 4 times 10 to the 26th joules. Watts are joules per second. And so that amount of energy, 4 times 10 to the 26th joules, is more energy than has ever been generated by the human race, like the entire human race in all of its existence. And by a long shot, right? It's not even close. And so that's just in 1 second. The sun pours out that much, way more energy than humans would ever need. But of course, we can only capture a small amount of that, right? Because it goes out into three-dimensional space. And then when it encounters the Earth, 150 million kilometers away, on average, there's only 1,400 watts per square meter on the surface of the Earth available. But of course, that's enough to grow plants and cause the weather and all sorts of stuff. You wouldn't want all that energy hitting the Earth at once. There would be no life on the Earth, right? So this 1,400 watts per square meter is perfect for living organisms on the planet, on the surface of our wonderful planet, on the surface and below the surface, below the surface. All right. Anyhow, the luminosity is remember, it's a nuclear event, or nuclear events, many nuclear events. But if you were to look at this, right, this amount of energy in 1 second, as it says here, it would be the equivalent of a billion, which we don't have anything close to that in the arsenal of the United States and the Russians and the Chinese, everybody who's part of the nuclear club. But 10 billion 1 megaton bombs going off each second. That's the equivalent of this 4 times 10 to the 26th watts. All right. So there's thousands of nuclear weapons, but nothing anywhere close to that amount of energy, obviously. All right, remember that what's going on is, as I mentioned, you have this 4 times 10 to the 26th watts, but then it gets spread out, right, in these, in a ever increasing sphere. And so by the time it reaches the Earth, that is spread out so much that only in 1 square meter, so you laid a meter stick on the ground, and then you put another one at right angles to it, where they were tip to tip, then that's 1 square meter, and so that's 1,400 watts. That's the amount of energy that's available. All right, so what about the sun's interior? We can't actually see the core of the sun, but we certainly know what's going on there. It's actually it's actually a very interesting place, and the center of the sun. It's tremendously dense. It's tremendously hot. It's much hotter than the surface of the sun, which remember is 5,800 Kelvin. So the thing about the sun, and stars that are stable, like the sun, is that it's in equilibrium. And it's in equilibrium with what, right? There's always, and they're representing this in green here, these arrows in green. There's always a gravitational force, right? Because you have the most, like 99% of the mass in the solar system is right here in the sun. And so there's this tremendous amount of gravity pulling all the matter in towards the center, right? Which is actually, that's a good thing, because that's giving enough pressure for nuclear fusion to take place. But there's got to be a balance. So there's an inward force, but that inward force has to be balanced. Otherwise, the star would be increasing in size and decreasing in size, or decreasing in size. And in fact, there are stars that do this. Not our sun, thankfully. We'll get to those much later. But this balance is sometimes called equilibrium, right? Or static equilibrium. Sometimes it's called. So it's where the inward force of gravity is balanced by the outward pressure, and the outward pressure is due to nuclear fusion that's taking place only in the core, right? That's where the nuclear fusion takes place. Because what we understand is, of course, the temperature and the pressure go up, and that's the only point where you can get 2 hydrogen atoms close enough. You have to have this tremendous pressure, tremendous temperature for 2 hydrogen atoms, which are basically 2 protons that don't want to be next to each other. You give it enough force or pressure, if you will. It's a very similar idea. For them to come close enough so that nuclear fusion can take place. All right, we've used Doppler, the Doppler effect to measure Doppler shifts, and we can actually see waves of basically sound waves rippling across the sun, which gives us other clues to its interior. The sound waves don't travel in a straight line when there's different densities, so that they will travel, and then when they encounter something that's a different density, that the sound waves will bend, and so we actually can measure that. All right, so this is our model. This is what happens as you get closer and closer to the center, and then right at the center, you get this tremendous. Okay, this just. Understand, this 150 grams per cubic meter is tremendous density. There's nothing that dense that you find on the surface of the Earth, right? I mean, the densest stuff you get is like, things like uranium, which is even more dense than lead, and uranium is down here at it would be down here around like 20 grams per. I think that's about as high as you find anything on the periodic table. So this is what's going on in the core, and we have you know, models you know, density and pressure models that tell us what the temperature and pressure would be if you have this much mass, and we know the force of gravity. We understand that quite well, actually, and that we can tell how much things are being squeezed. And notice the temperature, right? The temperature goes up tremendously at the center. Let's see what they're saying. So you know, it is in the millions of Kelvin, right at the center. So that, and of course, those things are required because you have all this mass, 2 times 10 to the 30th, concentrated in a region, and that is causing an incredible amount of gravitation, and right at the center that gravity is the highest, and therefore you get the highest density and you get the highest temperature, and therefore fusion is able to take place. Let's see, so this is the radiative zone. So after fusion has taken place, the photons are extremely energetic. They're generally in the gamma region of the spectrum, so they're extremely high energy. And then they encounter this convective zone, which is a cooler zone, and therefore what happens is the photons get absorbed. They get turned into heat, and convection is when a hot gas travels from place to place, and so that they bounce around. The hot material in the convective zone can bounce around in all sorts of random directions, but eventually that heat will reach the photosphere, and then takes off as sunlight. Right? That this is the sunlight that eventually reaches Earth. This is actually looking at in really fine detail at the surface of the sun. These are sometimes called granulations. You can see they're like little tiny cells, and one of these, here's a few of them that are about 5,000 kilometers across. So this is kind of a side view of 5,000 kilometers. And then you have the surface of the very surface of the sun, which is of course called the photosphere, and then the lower atmosphere, which is called the chromosphere. Right, and this is not like some smooth surface. There are things that they're like little flares that poke through the surface, and all right, so we'll see a little bit of that. So SOHO is a very famous satellite that has been in orbit and looking at the sun for a very long time. In fact, let me talk about this L1. So that's the first Lagrange point. I don't know. I just want to make sure that you guys have seen that. I think I pulled it up on. Yeah, here we go. Here's a nice picture of a Lagrange point. So this is from NASA's website here. Let's see if I can enlarge this. So there are 5 Lagrange points. These are points where the sun's gravity and the Earth's gravity basically cancel out. So L1 is a simple, that's the most obvious one. It's between the Earth and the sun. The gravity of the Earth and the sun cancel out right there. There's actually another one on the other side called L2. We've put satellites there that look out into the universe. There's another one called L3 on the opposite side, and these move, right? These 5 points move around as the Earth moves around the sun. So L3 is on the opposite side of the sun as the Earth, and I think it's actually a little bit further, if I remember correctly. It's a little bit further than the Earth's orbit, not much, but just a tiny bit. So L1, L2, L3, and then L4 and L5 are actually at, so if you took a line between the Earth and the sun and you went 60 degrees